basically with Lab 10, in my opinion, I would say it's kind of one of the easier labs. Um, and I would say somewhat more interesting than, the last few because they could be a little more like conceptual. But in this lab, it's like about machine learning and prediction. So you're basically going to be using training data in order to predict like outcomes. So we'll take a small portion of a data set in order to train an algorithm to make estimates on like a separate set of data, of test data. Um, and then one of the most important concepts in this lab in particular is the nearest neighbor, which is what I wanted to talk about specifically in this PowerPoint. So I will get started on that. So basically, in general, nearest neighbor or K, you'll see it as K in the lab for the most part. So just know what that's referencing. It allows you to use an already existing set of data in order to determine where a new piece of information would fit into the mix. And I took an example from chapter 17 of our textbook. If anyone hasn't read it, feel free to take a look. You know what I'm referencing. So we're basically going to use an example just to show you how to figure out what nearest neighbor is. So in this case, I will pull up a set of graphed data sets about patients with chronic kidney disease, or CKD. I might call it that for short because it's easier. So it's patients with chronic kidney disease, their hemoglobin and glucose levels. And we're going to use that information based on their levels in order to figure out um, if an undiagnosed patient has the disease based on their hemoglobin and glucose levels as well. And in this case, her name is Alice. So we're going to try and diagnose Alice basically. So you'll see two graphs. It looks a little intimidating at first, but I promise it's not. So the left side is basically just a plot of the entire set of data of all the patients who have um, chronic kidney disease. So they're in dark blue. You see them scattered throughout the graph. And then the yellow, the bottom right in the yellow, is those who do not have chronic kidney disease. And you'll notice that there is clearly a trend. So all the people who do not have it are bunched up in terms of their hemoglobin and glucose levels. So based off that alone, we can figure out, based on Alice's placement in this graph, if she would associate with those who do not have chronic kidney disease or who do. So on the right side, the right graph, there's a red dot, and that's Alice's numbers. And the black line that's pointing to is it's her quote unquote nearest neighbor. So the data point that has the closest set of glucose and hemoglobin levels compared to her. And based off just looking at this one nearest neighbor alone, we would say, oh, yeah, she probably does have chronic kidney disease because her numbers are more similar to people who have the disease, which makes sense, right? Um, but, just basing it off of one person might not be enough, or just off of hemoglobin and glucose might not be enough. So I wish it were that easy, but in this, we're gonna do a separate like look at patients with CKD as well, and you'll see this is white blood cell count versus glucose instead of hemoglobin, and you can see that the graph of the patients are a little harder to identify, like who would have or who would not have the disease, because you could see there are blue dots within the gold cluster in the bottom left corner. So people who do have chronic kidney disease, their white blood cell counts are similar to people who do not have it, which can make it hard for you to tell whether or not someone has chronic kidney disease from these two variables compared to glucose and hemoglobin. So technically, you could still predict what the outcome could be. You just can't do it with like 100% accuracy based on this given data in particular. The last one you could probably tell with a lot better chance of certainty. But this case, would be much harder to be 100% accurate. So, in order to um, compare Alice with more than one neighbor, we're going to look at multiple people to confirm her diagnosis, because obviously you don't want to base it off of one person. That would be kind of crazy if doctors did that. So we're going to pick a number for K being the nearest neighbor. So how many nearest neighbors we're going to analyze Alice and compare her numbers to. And typically you would pick an odd number, 3, 5, or 11. You can see I have examples up there. Typically they're odd to avoid like any ties of any sort. And you'll see we usually stick with like 3 or 5 in the lab in general when they ask you about picking a value for K. So we will do that. But the first thing you want to do is creating a test set. So we need 3 things for this. And I mentioned it earlier, a training set, in order for it to learn based off of given set of data. So we're going to take our initial chronic kidney disease data set that we had graphed previously, and we're going to use that data in order to train and also test on. So we're going to split it up. So, excuse me. So we'll have our training set, a testing set to actually try out our classifier that learned from the training set and see if it actually identifies correctly. And then we're obviously going to need a separate set of individuals that we don't know the status of their diagnosis. That way we can try and use the classifier to guess, hopefully, ideally guess correctly, as it did for the training set. So you can see the code down here. I wanted to give an example so you can see what I mean. So the first thing we would have to do is randomly use half of them for the training set and the other half for testing. So that's what the shuffled CKD is for. It's randomly shuffling all the rows, and we're going to take the first 79 because there's 158 rows in this total. That's why it's 158. So we're going to use the first half, the first 79 rows that it randomly mixed up. We're going to use that for training, and then the other half for testing. So just to explain that so it makes more sense. All right, and so you'll see we have our plot of our training data on the left here. You can just see this is what the coding looks like for it being plotted. So you'll see it's a lot less data points because obviously we're only using half of the data set. So this is what our classifier's using to train based off of this data alone. And then you'll see on the right side, this is like our decision boundary. It allows you to kind of place the test data over top of it to compare it to the training to see if it's accurate or not. So that's basically what we're going to do. We're going to graph the training data or the testing data, excuse me, and put it over top of this graph to see if our classifier is accurate based off of it using the training set. Hopefully that makes sense. All right, so this next slide, all the dots here are the test set that were placed over top of the training data. So we can see for the most part that our training data is good. There are a few mistakes because you can see a few blue dots in there with the rest of the yellow. So maybe there were some outliers in there that when the entire data set was randomized, it could have just kind of gotten lost in the mix and maybe it stayed mainly with the testing set instead. But for the most part, it's pretty accurate, thankfully. um, so, preferably. But yeah, let me just show you what that looks like. All right, so specifically, I wanted to look at the coding because obviously that's kind of why most people are here. So, you'll see right here, this top portion right here. I don't know if you can see my pointer, but it says Alice. So her levels are 0 and 1.1. So I just want to show that as a reference. But we also have a very, we need to create different functions for this as well. So we need to determine the distance. So we need a function that defines the distance between Alice and another point whose coordinates are contained in a row. So that's what this distance function is for with point 1 and point 2. It's pretty simple. It's just point 1 minus point 2 squared and then the square root, which are like, maybe you're like, wow, why are we doing that? That doesn't make sense. It's just to avoid if it was a negative number, it would mess up the subtraction if we just let it be point 0.1 minus point 0.2. So that's why we're squaring it and then doing square root. So that way we can find the distance between the 2 points without having to worry about any negative numbers. So we'll use that to define distance from Alice, which will take its row as an argument, return the distance between that row and Alice. Just want to make sure I have everything right. So that'll be this part here, the distance from Alice, because once we know the 2 points, we can use that in this next function to determine how far away that neighbor is from Alice, and then we can organize them for multiple neighbors you'll see down here. So these are all multiple different neighbors from Alice, so we can kind of compare them and see, organize based off the ones that are closest to her. So this is just the general graph or the general table, but now we need to sort it by descending order. So we'll see up here, I just did dot sort, and now we have the lowest number at the top. So these are the closest neighbors to Alice. And if we wanted to say find k equals 5, we would just do, the first 5 rows. So the 5 closest neighbors to Alice are these 5 at the bottom right. So yeah, hopefully that coding makes sense. But I just wanted to give you guys a look at like what the coding process would be like and like how it comes together. And if that doesn't make sense, please like ask questions. And I want to make sure I'm explaining this so that everyone understands what I mean. But basically, you're finding the distance between 2 points in one function, and then you're finding the distance from Alice based off of that. And we're going to put that into a new column and apply it to her nearest neighbors. And that way we can identify which plots are the closest to Alice, and that's how you would identify the nearest neighbor. So hopefully that helps. And then lastly, I just want to show you what this looks like on a graph, so that way we can see it visually. Because I know sometimes it's hard to tell just based off looking at it, like a data set, like a table. So this is the top 5, right? And they're all located within this green circle. So that way you can see what it looks like. So obviously we see 3 blue dots that are close to her. So like, oh, those are people with CKD. So, thinking that way, oh, she would be diagnosed with it. But there's 2 that are gold that you can see in the table as well, which can be a little confusing. But based off the fact that the top 2 closest are dark blue and have the disease, we would predict that Alice would also have the disease based off that data. So in the end, using one nearest neighbor was enough to diagnose her properly, but if we wanted to be even more certain, it made more sense to use more nearest neighbors that way. I mean, if we had just done 3, we would have came to the same conclusion. If we had done 9, we may have or we may not have. It honestly just depends. But based off of the 5 nearest neighbors we had, we would confirm that she does have CKD. And hopefully that kind of helps you understanding in what nearest neighbor is for. Basically, given a certain set of information, where would Alice be? Like, I fit into this set of data more of what it would be about. But hopefully that makes sense. If anyone has any questions or anything, please let me know. I'd love to clarify if possible.